They come in all different sizes and designs.
Burning all kinds of fuels, they power and energise our modern lives. In today's episode, we're lifting the hood on engines. Welcome to the programme. Rarely has an invention had a greater material impact than that of the internal combustion engine, or ICE. Since its birth in 1859, it's become an integral part of the very fabric of our modern world, powering most of the estimated 1.2 billion vehicles on the planet and many other industries and processes besides.
The technology that provided seemingly limitless power and freedom to travel has changed little in well over 100 years. But for a sustainable future, it could be time to change gears. Ashley, what's powering this episode?
Well, big engines, which usually means big pollution. But maybe it doesn't have to be that way. How old technology helps to power the new in an innovative new ship. And taming the power of the jet. Is aviation on the cusp of a new revolution?
As usual, we had some help from an expert in the sector. Professor Simone Hochgreb of the Department of Engineering at Cambridge University will help us demystify these vital machines.
Now, an engine or a motor basically converts one form of energy into mechanical energy. And the problem that faces us today is how to do that more efficiently if we want to continue powering our economy in the way we've become used to.
The global average annual improvement rate of fuel economy has remained close to 2% per year since 2005. Air travel gets a bad rap, but most automobiles use anywhere between 5 and 15 litres of fuel per 100 kilometres of distance travelled, whereas a modern full passenger jet aircraft can achieve an efficiency of around 2 to 3 litres per 100 kilometres on a 9,000 kilometre flight.
A very robust and reliable engine designed by German inventor Rudolf Diesel is ripe for a makeover. We visited a facility in the US that is hoping to drive forward that revolution.
Greenhouse gas emissions from the transport sector have more than doubled since 1970, increasing at a faster rate than any other energy end-use sector, and road freight is a large part of that. In the US, California tabled some extreme low pollution goals, a figure that is 90% below the current standard. And one US engine manufacturer has risen to the challenge.
We've been working on engines for 17 years now. I would say for the last 7 years, we've been looking at near zero emissions, predominantly for Euro 6 certification. The last time around on emissions regulations, the 0.2 gram NOx regulation, that's where the industry basically stopped. California said that's not clean enough for us, so they opted for 3 optional levels, which was half again as low, 0.1 gram, which is where our 6.7 liter is certified. Half again as low as that would be 0.05 grams, and then again half again is 0.02 grams, which is where we certified the L9N and the ISX12N.
To provide an engine that could power a large vehicle and hit the emissions target meant switching fuels from diesel to gas.
So natural gas is a fossil fuel sourced out of the ground. It burns very clean because it has very little carbon in it. And recently now we have renewable natural gas that we can continue the sustainability of the fuel through landfills and waste products to use the fuel for power.
But diesel engines have been king of the heavy goods vehicle market for good reason, producing high torque at low RPM. Can gas compete?
The fuel density, the BTU content is lower in natural gas, so we can't achieve the highest ratings that diesels can. But below that, all the ratings below peak power, they're almost identical. So the engines are very similar in performance, and the seat of the pants feel to the driver.
In engineering terms, the gas engine shares 80% of components of the diesel counterpart. But the gas engine is designed to produce what they called stoichiometric cooled exhaust recirculation.
Stoichiometry, that is actually where we have the right amount of oxygen to have complete combustion, which means we don't have any excess oxygen or excess methane. So the advantage of that is you're running your cylinders relatively cool, so the likelihood of forming oxides of nitrogen is reduced significantly.
And to keep the engine working at peak efficiency, it contains an electronic control module.
Now, we use the ECM to control the combustion process, to control a number of things on the engine that reduce emissions and keep us a very hospitable engine in the marketplace.
And the engine is flexible. It can run on a variety of gases.
The different fuels that we are using are natural gas, the normal natural gas and the renewable natural gas. And in liquid form we use LNG.
So a government incentive has produced a real and positive outcome, and one that hopefully this and other manufacturers can profit from, while also providing a cleaner and healthier transport for us all.
Simone Hochgreb is a professor in Cambridge University's Department of Engineering. She works in the area of energy, fluid mechanics and turbo machinery, and teaches on combustion, internal combustion engines, heat and mass transfer. Previously, she's worked at MIT, Sandia National Laboratories and an engineering consultancy firm. Simone, thank you so much for having us here at the University of Cambridge. Firstly, tell me a little bit about yourself and what you do here.
I'm a professor of engineering, and my area of research is combustion. Combustion is burning things in engines, gas turbines, power generation from fossil fuels. So my job is to try to make all of these devices cleaner and more efficient.
Tell me about some of the major efficiency gains in internal combustion engines.
Yeah, so the principles are still the same. You still have a cylinder and then a piston inside it going up and down and so on. What has changed since the invention of these engines, the efficiencies have gone from maybe 5% to now close to 50% of these engines, which is approaching, let's say, potentially the limits. And what has changed is that now you can achieve higher compression ratios, so that's really where most of the efficiency gains are. And then you have hybridization now, which is a combination of what the engine is doing with what the battery is doing to try to, in one package, get very high efficiencies.
Tell me what's in the research pipeline right now, but also what can be coming up in the future.
Right, so the transition now is that many engines are being hybridized. They're becoming smaller, so whereas before what was cool is to have a car with an enormous hood, an enormous engine, now they're becoming smaller and smaller, but very high pressure, so they're turbocharged, downsized, and they are being designed to work with the hybridization. So that's one of the trends that's going on. There's still more controls going into it, more hybridization, and with the automation that's going on in terms of self-driving car, they're starting to look more like completely automated devices, let's say, that will drive and choose the operating conditions for the engine.
What about onboard chips and computers? How have they improved efficiency, and what more can software do?
So right now these engines have to have controls that automate not only their operation in terms of the engine and what's going on with the battery, and what's going on with the after-treatment system, but they also have to work very fast. So on the fly, almost on a cycle-to-cycle basis, there are decisions being made about which things have to be turned on and off to give you the optimum in terms of the performance of the engine from the point of view of the consumer. If you have to overtake the truck, you will, but at the same time, you also have to think about whether your emissions are optimized and whether your efficiency is optimized within the whole system. And that has to be done in a very, very short time scale. So we're looking at almost cycle-to-cycle control of the system.
The environmental cost of huge marine engines has been well documented in this series, but the accompanying cost to owners is less well known. In Sweden, we jumped aboard a ship that should be cleaner for the environment and cheaper to run.
Stockholm, capital of a country with a long seafaring tradition and a regular stopping point for a new type of cruise ferry.
The Viking Grace is a passenger cruise ferry operating between Turku in Finland and Stockholm in Sweden. We carry a maximum of 2,800 passengers. The ship is 218 meters long and carries both passengers and cars and freight.
But this ship has a few adaptations that make it rather special. And a key one is in the ship's bowels.
The Viking Grace is powered by 4 main engines built by Wärtsilä, the top modern combination diesel and gas. We use gas as the fuel, but we have a spare system for diesel in case of problems with gas supply or something. Each engine has over 10,000 horsepower.
The Viking Grace is actually the world's first large passenger ship that uses liquefied natural gas, LNG, fueled engines.
The benefits with LNG is that the emissions are up to 85% lower than with an ordinary traditional diesel engine. So the sulfur emissions are much lower.
LNG use for marine engines is relatively new, so infrastructure has had to be updated.
The LNG requires a distribution system. We have a dedicated fueling vessel that visits the ship in Stockholm 3 to 4 times a week to top up the fuel tanks.
Above deck is another innovative engine that harks back to the days of sail and relies on a principle called the Magnus effect.
If you play ball games like football, tennis or golf, you might note that when you have a spin in the ball while it's flying through the air, it's not flying straight anymore. That's caused by the spin of the ball, which is creating a pressure difference between the sides of the ball, and that is the Magnus effect.
The technology was developed by a Finnish company from an original concept developed in the 1920s.
When we rotate a rotor sail, air starts rotating around the rotating rotor, and when that rotating air is interacting with the sea wind, the Magnus effect takes place. So the entire rotating cylinder starts pushing forward the ship. It becomes a mechanical sail, which is reducing the main engine load, the fuel consumption and all related emissions.
Viking Grace has only one rotor sail, but with more of them, the efficiency improves.
We take electricity from the grid of the ship to rotate the rotor sail. And when we spend 1 unit of electricity to the rotation, in average we produce 14 units of forward thrust.
And how has that affected the Viking Grace?
Our decision to test this technology is based on the simulations that show that we can save up to 300 tons of fuel, meaning we can cut CO2 emissions with 900 tons a year.
So one ship is showing that by combining old and new propulsion technologies, we should still be able to plough the seas.
Simone, the challenges for transport at sea is very different from that on land. We saw some amazing innovations in that piece there, but how can we improve efficiencies in these mammoth engines?
So the principles are still the same. You want to have very high compression ratios so you can achieve the maximum efficiencies. But now the volumes are much larger, so you still have to mix the fuel in the air or the unburned stuff with the burned stuff in a much larger volume over still times they're commensurate with the speeds of the engine. So achieving that balance between very high mixing, very low speeds, and burning everything at very high pressures is where the balance will be here. You have very high strains on the engines, and somehow you have to generate the turbulence at very low speeds.
Maritime pollution is a real problem. How can we burn these fuels more cleanly and scrub the residue more effectively?
One of those very large ships can produce way more pollution than a single car. In fact, tens of thousands of cars would be equivalent to what one of those large ships at port would produce in terms of pollution. So it's a very important problem, and there are new regulations coming in now to try to change the fuel a little bit, which will improve the quality, but really the large improvements would have to be made by changing completely the fuel, because unlike small engines, it's much harder to make these engines operate very efficiently.
Because they're so big.
Exactly, because it's hard to mix the fuel in the air and burn everything up and get rid of the particulate matter typically and NOx, which are the ones that appear for these very large engines. So if you're looking at liquefied natural gas, for example, that's a potential very good fuel for some of these large engines. Of course, then you have to carry the liquefied natural gas. And so, whereas that's completely normal for a tanker carrying natural gas, much harder to achieve for a normal container ship. So there are changes coming on now for the fuel itself, and there are manufacturers who are working on trying to make or incorporate some of the advances that have been made with smaller engines into the larger engines. But a lot of engineering is going to have to be done in order to achieve that still.
Thank you so much for that, Simone. Stay with us. Now, think you know everything there is to know about new engines? Here's one common misconception.
You thought you knew? Think again. Myth: when the oil in your engine goes dark, you should change it. Fact: engine oil is designed to hold engine wear particles in suspension. Being dark just means it's doing its job. Modern engine oils contain detergents that help hold these particles and stop them building up on the surface of the engine. Of course, the oil is limited in how many of these suspended particles it can contain, and will eventually need to be changed when it becomes saturated. So, use the oil change interval recommended by your car's manufacturer to decide when to change it, not the colour of the oil on the stick.
Aviation produces around 2% of global greenhouse emissions, which are expected to rise at about 3 to 4% per annum. But the industry is not standing still. So we went to Derby in the UK to visit one of the world's largest jet manufacturers and see how they're hoping to keep us flying sustainably.
Rolls-Royce is synonymous with the history of aircraft propulsion, from the famous Merlin engine that powered the Spitfire during World War II, to the Schneckmer Olympus 593, which powered Concorde. With such a strong legacy, it also has an eye on the future and aviation's responsibility to become greener.
Passenger numbers globally are increasing over 4.8% per year. And so it's vital that whilst aviation is only 2% of global man-made CO2, that we do our bit to drive down the emissions of our engines. And right now we're able, with very advanced technology, to improve the efficiency of our products by 1% per year on average.
The mainstay of aviation propulsion is the jet engine, and the concept has been around for almost a century, but has changed little.
Right at the front of the engine is a large diameter fan that sucks in a huge volume of air and passes that air further back down the engine. So if we move towards the centre section, the gas turbine section of the engine, in the centre here, that air is provided to the compression system where it's squeezed to high pressure. We add fuel and burn to produce an excess of energy. And then in the turbine, we blow that hot, high-energy exhaust system through the turbine and out of the back of the engine. The turbine has two roles. It extracts energy to drive the compressor and the fan, therefore to provide the suck and the squeeze. And the fan drive is actually providing 95% of the thrust that an engine like this would operate to and provide to the aeroplane.
But the original jet engine was designed to provide power rather than be environmentally sound. Here in Derby, however, they're working on a new breed of jet engine that could seriously improve the environmental credentials of jet travel.
The Ultrafan engine is going to offer about 25% fuel burn improvement relative to the first generation of Trent engines that Rolls-Royce produced. That's a major step forward. As well as burning less fuel, that obviously means less emissions, whether it's carbon monoxide, nitrous oxides or particulates, and less noise as well.
A key change to this jet engine is something we're more used to in a car than a jet: a gearbox.
The Ultrafan engine features a power gearbox that allows us to run fan and turbine at optimum speed and optimum efficiency. To achieve that, we have to design and make a gearbox that transmits 70,000 horsepower while being light enough to carry in an aero engine. That brings a lot of challenge.
The temperatures and environment within the jet engine are very extreme, so the team face extraordinary engineering challenges.
So to make a modern jet engine as efficient as it can be, we have to push the internal conditions in the engine pretty hard. That forces us to use exotic materials to achieve the running conditions of the engine. In the high pressure turbine, for instance, we'll be using metallics and ceramics well above their melting point. Temperatures as high as 1800 centigrade around the HP turbine, pretty extreme.
The fan system at the engine intake will also be different, with a capacity more usually found in propeller aircraft.
Our first generation UltraFan features a fixed pitch carbon titanium fan system, but future generations of UltraFan will feature a variable pitch. So we're able to adjust the incidence angle of the fan blade to match the operating condition of the engine, and potentially to eliminate thrust reverser components, which represent a lot of weight to be carried around by the engine throughout its flight cycle.
Designing and testing such an important mechanical device takes time, as the engine needs to be very reliable as well as efficient.
Our demonstration UltraFan is expected to fly in about 2023, and if we're looking at a product that flows from that as early as 2025 or through the latter part of 2020, that's when an UltraFan would become a passenger carrying product.
But more long-term, could the future be electric?
One of the ways in which electrification is impacting aviation is in creating a new type of aircraft for regional aviation, a so-called regional hybrid electric. And eFan-X will be the world's first demonstrator of hybrid electric technology aimed at passenger aircraft.
The extraordinary history of flight has allowed us all to break the bonds of Earth. Hopefully, continued innovation will allow us to protect it a little more too.
Jet engines really take design to the limit. Now, I gather that some of the temperatures in the engines are higher than the melting temperatures of some of the parts, but the design keeps the parts cool. How can hardware keep evolving and improving in this way?
Yeah, so that's right. You're pushing the limits there by increasing the pressure ratios so that the efficiencies that you can achieve are higher and higher. And that means that by the time the combustion ends in a process like that, the temperatures are higher than what the material can take. What you do then is you engineer air coming back from the compressor to cool part of the engine, and the trade-off that you have then is keeping the material alive at very high temperatures by using these tiny little holes to keep blowing over the gas turbine blades to produce the power. Now, materials are evolving continuously, and so what wasn't possible until maybe a decade ago now is still pushing the limits of understanding how these materials work and still keeping them cooled so that the temperatures can be slightly higher all the time. We haven't quite reached the limit.
What other technological advances have we seen in aero, and will we ever be able to travel sustainably in the air?
Well, it depends on what you mean sustainably. Okay. So if we're talking about producing fuel sustainably, for example, that solution would be available now. So if you could produce, for example, a fuel that looks like what you put up in a plane now, then you'll be able to burn it and fly sustainably. And one of them is our Fischer-Tropsch type fuels and so on, which are very similar to jet fuels that you might have.
And do we use them now?
They can be used. They're too expensive at the moment, and they take too much energy, let's say, to produce them. But in principle, it's feasible. Likewise, with hydrogen. Could we use hydrogen, for example? Yes, you could use that. You have to redesign the engine to some extent because you'd have to carry the hydrogen in a different form. But they can be burned and they can be used. So it very much depends on how you produce those fuels and are they sustainable. If you're talking about electricity, however, and batteries, does that make sense? Well, because of their weight. At the moment, that doesn't make sense. If there are breakthroughs in energy storage, potentially that's the case.
Thank you so much for having us here today, Simone. It's been a pleasure.
You're very welcome.
The word engine comes from the same Latin root as the word ingenious, and there's no doubt that the developments we've been discussing in this episode of Sustainable Energy have provided a real revolution for us all. The challenge now is to continue that ingenuity and power us on in a more sustainable and cleaner way. Next time, we'll take a look at what sustainable mobility means in the developing world, and there could be some surprises.
That's right, Ashley. So if you have any questions for our next expert, start tweeting now at CNBC Energy using the hashtags AskSE and Sustainable Energy.
But that's the end of this journey, so until we start our engines again next time, keep thinking green. Goodbye.
Goodbye.